Hello everyone. So in this video we are going to discuss again a very important theorem of modular arithmetic that is known as Fermat's little theorem. So this is just to know about the primarity testing of any number, like with the help of this theorem up to some extent we can test a number is prime or not. So this is known as Fermat's little theorem. So we are going to know what is the statement of Fermat's little theorem, and also we are going to prove this Fermat's little theorem. So Fermat's little theorem says let P be a prime, let P is a prime number, P be a prime and A be any integer. So there are two numbers A and P. P is prime and A is any integer such that GCD of A and P is 1, or you can say A and P are co-prime to each other. GCD of, which implies GCD of A and P is 1. Then A raised to the power P minus 1 will be congruent to 1 mod P. So this is the statement of Fermat's little theorem. If P is a prime number and A is any integer such that A is co-prime to P, then A to the power P minus 1 will be congruent to 1 mod P. So now this is the statement, and now we are going to prove this, that how this comes to be true. So proof we can give it like this. For example, we need to find out ZP. So ZP will be the set of all the residual classes. So 0, 1, 2 up to P minus 1. So now you all know that what is ZP. ZP is the set of all residual classes, and when I talk about ZP star, it is going to be ZP minus 0. So now the ZP star will be 1, 2 up to P minus 1. And what is 1, 2 up to P minus 1? Let's say there is a set R which is known as 1, 2 up to P minus 1. So set of real numbers, set R. So this is, this is not, do not confuse this. This is, we can say this is reduced residue system. This R is known as reduced residue system under mod P. So we can write it like this. So since this P is a prime number, so since we know that P is a prime number, this A capital R will be AR, where R belongs to capital R. So it means we can write this A capital R will be, AR means A into 0. Sorry, 0 we have removed from here. So this is R 1, 2 up to P minus 1. So this A capital R will be A, 2A, 3A up to P minus 1 A. So up to P minus 1 A. Now what we have to prove? Our claim is we want to prove that this A capital R should be equal to R in any order. Or doesn't matter what is the order, but this A cap, we will prove first that this A capital R is equal to small r. So to prove that, suppose, so this is our claim, or this we want to prove. As of now, this we want to prove. Once we will be able to prove this, we will be able to prove this statement also, the statement of Fermat's little theorem. So just to prove this, let's suppose we have two numbers and we write NA is congruent to MA mod P. So when we write NA is congruent to NA mod P, NA is congruent to MA mod P, then it is possible only when N and M are same. N and M should be same for this. And what we know that A is congruent to P. If A is congruent to P, then we know that A inverse mod P exists. A inverse mod P exists. Then only A can be congruent to P. So when A is congruent to P, then this is like a necessary condition that A inverse mod P exists. So we can write N A into A inverse is congruent to M A into A inverse mod P. So A into A inverse and A into A inverse is going to be 1. So here we can write n is congruent to m mod p. And when we write n is congruent to m mod p, we know that we have proved this n and m are same number. So when n and m are same number, we can say that a, for this a, 2a, 3a up to p minus 1a, they are congruent to 1 comma 2 comma up to p minus 1, because they all are like a, we can consider a and p is prime, they all are congruent in some order, are congruent to 1 to p minus 1 in some order. What does it mean? It means like maybe a is congruent to 3 or 3a is congruent to 2. Order is not same, but all the number of this first one are congruent to this in some order. So if we are writing this, it means AR is equal to R. It means A of capital R is equal to R. So up to now we have proved this. So let's write it A, 2a, 3a up to p minus 1 a, if it is equal to 1, 2, 3 up to p minus 1 mod is congruent to this mod p. So we can write a to the power p minus 1 from here, a to the power p minus 1, and 1, 2, 3 up to p minus 1 can be written as factorial of this p minus 1, and here it is congruent to factorial of p minus 1 mod p. So when we write factorial of p minus 1 mod p, and what we know, let's say this p minus 1 factorial is equal to a number x, and we say that x is congruent to p because p is a prime number. Why x is congruent to p? Because p is a prime number. This we have in our assumption, we know that p is a prime number, and x contain all the number which are less than p, like 1, 2 up to p minus 1. So x will be congruent to p. For example, let's say we have a number 5 which is prime number, and any other number which is less than x, like 1, 2, 3, 0, 0 is not the member, 1, 2, 3, 4, which is less than x, that will be congruent. GCD of these numbers will be 1. So we can say that x is congruent to p. Now if x is congruent to p, can I write it like this? This is a to the power p minus 1. I am writing this equation in the form of x. So a to the power p minus 1 x is equal to x mod p. And we know that x is congruent to p. It implies x inverse exists under mod p. Under mod p. So we can write a to the power p minus 1 x inverse is equal to x inverse mod p. So here this is 1, this is 1. We can write that we come to know that a to the power p minus 1 is equal to 1 mod p. So this is how we prove Fermat-Settle theorem. So this statement of Fermat-Settle theorem is quite useful for many like block ciphers or encryption standard schemes. So that's why I prove it here. You should know that how it comes to be true, and in the later videos we will do some numerical or some questions also to in which we will use this Fermat-Settle theorem. Okay, so that because this is very important theorem, and you should all know about this statement. If a and b are co-prime, then a and p are co-prime, then a to the power p minus 1 is equal to 1 mod p. And we have already proved this, that how it comes to be true. So we simply define ZP. ZP is set of residual classes and ZP star. And when it becomes ZP star, we reduce it, write it like 1, 2, 3 is reduced residue system. And for this reduced residue system mod P, we put a symbol R. And in the next term, we write AR is equal to set of A into small r, where small r belongs to capital R. So AR becomes, because capital R is 1, 2, 3 up to P minus 1. So this AR becomes A2, A3, AP minus 1. And then we prove how this A capital R is equal to capital R. And after proving this, we prove the statement of Fermat's Theorem also. Thank you.